We continue with our discussion on force on a plane surface submerged in the fluid, and we take up the same example that we took in the last class, and we will try to find out the force on this surface by direct integration without going into the standard expression for force. So, here if we recall, what is the objective of this problem is to solve that what is the force that is required to keep this gate stationary, and to do that what we required is to find out the moment of the distributed forces acting on this semicircular plate with respect to the hinge point O. That was the one of the objectives for writing the equation of equilibrium with respect to the rotational equilibrium. So, to do that what we can take a small element. So, when you take a small element here, you have to consider a radial and a circumferential element simultaneously. So, we can consider a small element shaded like this. What is the specification of the small element? It is located or centered around r comma theta. That means we consider that this is located at a radial location of r and angular location of theta. The angle subtended by the element is d theta. The radial location is small r, which is the radial location of the element. The radial width of the element is dr. So, what is the differential area that is being represented by the element? Yes? No question of 2 pi, right? It is just shaded element, the shaded area. So, it is like roughly like a rectangle. One of the sides is r d theta, another side is dr. So, r d theta dr. What is the force that acts on this element due to pressure? What is the pressure acting on this element? So, it is related to the local height of the element. What is this local height? So, capital H is the total height minus small r sin theta. So, the force acting on this dA, that is dF, is equal to H minus r sin theta into rho into G into r d theta dr. What is the moment of this force with respect to O? So, this into r sin theta. So, if we can break it up into two terms, multiply this by sin theta r sin theta. So, it will be H r square sin theta minus r cube sin square theta, that into rho G d theta dr. Now, the total moment of this distributed force with respect to the point O is integral of this dm. Now, when you consider the integral is with respect to both theta as well as r. It is a double integral. So, you may evaluate the integral with respect to r first or theta first, it is irrelevant. Let us say that you want to evaluate the integral with respect to r first. So, you have first the integral with respect to r. So, when you have integral with respect to r, small r varies from 0 to capital R. So, the first term becomes, this is r square dr, that means r cube by 3. So, this we are integrating with respect to r sin theta minus, this is r cube dr. So, r to the power capital R to the power 4 by 4 sin square theta d theta. Now, integral with respect to theta. What is the limit of theta? 0 to pi. So, the remaining work is very simple. I need not complete this one. These are very simple integrals and you can complete yourself. So, once you complete this integral, you will get an expression for resultant moment of the distributed force with respect to O in terms of H, capital R, and of course rho and G, and this resultant moment is equal to what? Capital F into capital R. So, that will tell you what is the value of capital F. Okay. We have seen that why it is so, because all other forces acting through it will pass through O. So, they will have no moment with respect to O. So, this is just like these are the two counteracting moments. So, this example shows that whenever you have force on a surface, it is not necessary that you have to go by the formula that we have derived. You may as well take a small element, consider pressure distribution over the small element and find out what is the resultant force due to that pressure distribution, resultant moment and so on, by fundamentally integrating it over the entire area without going into the formula. Okay. Next, what we will consider is force on a curved surface. Now, can you tell me that what is the fundamental difference, or what you expect the fundamental difference to be as compared to the force on a plane surface? How you expect force on a curved surface to be different conceptually? Force on a curved surface. Again, what is this surface? This is immersed in a fluid at rest, so that we are not repeating. So, the surface may be something like, let us say the surface is something like this. Again, if you see, this surface is actually something like this, okay, and there is some fluid on one side and that fluid is exerting some force on the surface. So, this is again edge view of the surface. Earlier we were concentrating on force on a surface like this, which is a plane surface. Now, it is a curved surface. So, you can understand the geometrical difference, that is fine. Fundamentally, in terms of basic mechanics, how do you expect these to be different as compared to that for force on a plane surface? Force direction changes as you move from one point to the other point. That means it is not a system of parallel forces. So, the plane surface has to deal with a system of parallel forces. So, you can treat it like a scalar addition problem or a scalar summation problem, whereas in this case it is having the pressure always acting normal to the boundary. Normal to the boundary is a direction that is changing from one point to the other, and therefore, the resultant force is being dictated by a varying direction of the surface. So, you no more have a system of parallel elements which is giving rise to the resultant. So, whenever you are adding here that to make the resultant force, it has to be a true vector addition. It is not just by adding it up in a scalar way. Integration is nothing but summing up the individual components, and you could see that a very simple integration could give the same result for force on a plane surface. For a curved surface, therefore, fundamentally the principle is the same, that is you take element of the curved surface, you find out what is the force acting on it, the force acting on it will be normal to it, you may break it up into components, horizontal and vertical components. In this way, for each of the elements you can find out the horizontal and vertical components, algebraically sum them up and make the vector addition. So this is something which is very trivial. Now it is possible sometimes to reduce the calculation a little bit by taking some help from the concept of force on a plane surface, and let us see how. Just consider that there is a fluid column like this. This is a volume of fluid which we are considering to be located within the projected part of this curved surface. So if these curved ends of the curved surfaces are projected to the free surface, whatever volume is contained within that, that contained volume is enclosed by this dotted line. Okay. Now let us say that we are interested on the forces which are acting on this volume of fluid. So this volume is now having two plane surfaces, three plane surfaces, but forget about the top surface, just for the time being consider the side surfaces. So if you consider the volume say A, B, C, D, the surfaces A, B and C, D are plane surfaces, and let us see that what are the forces which are acting on these plane surfaces. So we are essentially trying to draw a free body diagram of the volume element which is enclosed by this dotted line. So what are the forces which are acting on this? So when you have the left face, there is some fluid towards the left of it that exerts a force due to pressure. What will be the direction of that force? Let us say we set up coordinates like this, x and y. So what will be the direction of that force? X. So we call it a horizontal force, assuming that x is a horizontal direction. Let us say that Fh or Fh1 is the horizontal force acting from the left towards this element. Similarly, if you have some fluid again on this side, there will be a horizontal force say Fh2 acting from the other side towards this. Remember, this force is due to pressure, it is compressive in nature. So whatever is the fluid element located on the other side, it is having a tendency to compress it, and that is how the senses of these vectors are there. These are the horizontal components of the forces on these sides. What are the additional forces on this element? It should have its own weight. So whatever water or fluid is contained here, that will have its weight say W. Any other force? Yes, there is a reaction between the surface and the fluid, and that reaction again is likely to have two components, one is the horizontal component and another is the vertical component. So let us say that it has a horizontal component Fh and a vertical component Fv. What are these? These are the components of the reaction forces exerted by the curved surface on the fluid. Okay. Now the fluid is in equilibrium. So when the fluid is in equilibrium, you must have resultant force along x equal to 0. So you have Fh plus Fh1 minus Fh2 equal to 0. That means Fh is equal to minus of Fh1 minus Fh2. Okay. Then resultant force along y equal to 0, what it means? Fv minus W equal to 0. That means Fv equal to W. From this apparently very simple calculation, we come up with a very interesting result, that is if you have a curved surface, still whatever forces which are acting on it, you may resolve it into two components. For the horizontal component, it is basically the resultant force on the horizontal projections or on the projections of these curves, ends of the curves on a vertical plane, or so called horizontal components of the forces on vertical projections of the end of the curve. That means if you have a curve like this, when you consider the end, this end when you consider its projection, the projection is just like this. So we are basically having to consider a horizontal component of force for the left, a horizontal component of force for the right, and the difference of these two is actually giving the horizontal component of the net force. For the vertical component, it is just the weight of the fluid that is being contained within this extended volume. So if you somehow can calculate the weight of the fluid, and that is as good as calculating the volume of the fluid, because then you can use the density to calculate the weight of the fluid. So whatever fluid is contained here within this dotted line, weight of that fluid is the vertical component of the force, and whatever is the horizontal component of force, or whatever is the force because of pressure on the projections from the taken from the sides of this curve, that contributes to the resultant horizontal force. And remember that these are the forces exerted by the curved surface on the fluid. We are interested in the other thing, the opposite thing, that is what is the force on the curved surface. So by Newton's third law, those are just negatives of this one. So minus Fh and minus Fv are the forces which are exerted by the fluid on the curved surface. Okay. Let us take an example to see that how we calculate it. Let us say that we have a long circular cylinder and you have the free surface of the fluid in this way. So on the left side this is the free surface, on the right side this is the free surface, and the solid material is a circular cylinder, long, its length is perpendicular to the plane of the board. We are interested to find out what is the resultant horizontal and vertical component of force exerted by the fluid on the cylinder. Okay. So what we will do is we will give some names of, or we will give some markers to important parts of the surface, say the 4 important points A, B, C and D, and we will consider the forces acting on this curved surface one by one. So first let us consider the force acting on AB. First let us consider the vertical components of forces, then we will do the horizontal component. So for vertical component, what we want, we should raise projections from the end of the surface till it reaches the free surface. Whatever is the volume of the fluid contained within that, it is the weight of that, fine. So for the part AB it is like this. Next let us consider the part BC. So when you consider the part AB and you know the vertical component of force, is it downwards or upwards? It is downwards. I mean from common sense it is clear that the pressure is being exerted in such a way that its vertical component is downwards. Now consider BC. So for BC what we do, again we raise the projection from one end, it is like this, from C we raise the projection up to the free surface. So whatever is the volume that is contained within this. So what volume is contained within this? This is the volume that is contained between BC and its projected parts up to the free fluid surface. So, this is an imaginary volume of fluid, right, and what will be the direction of the vertical component of force acting on it, upwards or downwards? How do you make it out? Just see that if you have BC like this, you will have the pressure acting on it in this way, its vertical component will be upwards. So, it is such a distributed pressure over BC. So, look into the fundamental origin, that will give you the guideline whether the resultant force is upwards or downwards on that part of the surface. Now, when you consider these two together, you can see the common part which is shaded, once it has come downwards, another it has come upwards. So, they have cancelled out. So, what remains is the fluid equivalent to the volume of half of the cylinder for this half part. So, what is the vertical component of force acting on say ABC? It is nothing but the equivalent to the weight of the volume of half of this cylinder. Weight of what? Weight of the fluid equivalent to the volume of the half of the cylinder. So, that means as if it has displaced a fluid equivalent to its volume and that is exerting it an upthrust. So, this is nothing but the Archimedes principle that you have learnt in high school physics. So, in effect what is happening, when the solid is being immersed in a fluid, it tends to displace a volume of fluid which is equivalent to the volume which is immersed, and that tends to exert an upthrust, net upthrust, and that upthrust is nothing but same as the weight of the displaced volume of fluid by that particular volume of solid. Now, if you come to CD, so for CD how you calculate the force, vertical component of the force? So, you extend it up to the free surface. So, for this part the free surface is up to the level shown. So, it is nothing but the volume of this much. So, is it upwards or downwards? It is upwards. So, if you have the pressure acting in this way, its vertical component will be upwards. So, the resultant is upwards with what magnitude? If r is the radius of this cylinder. So, what is the volume corresponding to the left part, that is pi r square by 2 into say L, where L is the length of the cylinder. Then this part is pi r square by 4 into L, this is the volume, that multiplied by the density of the fluid, not density of the cylinder but density of the fluid, into G, and acting upwards. So, this is the resultant vertical component of force. How can you calculate that? What is the location through which the resultant of this force passes? So, it will definitely be passing through the centroid of the displaced volume, and then it boils down to the calculation of the displaced centroid of the displaced volume. We are not going into that, you can do it by simple statics. How do you calculate the horizontal component of force? So, again you have something in the left and something in the right. So, when you have this ABC, on ABC what is the horizontal component of force? Let us say that is FH1, just following this symbol, and on CD there is a horizontal component of force, say that is FH2. So, FH1 is what? What is its projected area on which you are considering that, because this is now equivalent to force on a plane surface. So, 2r is the height and L is the length. So, its projection on the side view is 2 2r is its height, because 2r is the height of the cylinder and L is its length perpendicular to the plane of the figure. So, if you recall, what is the resultant force? Rho of the fluid G into A. What is A? 2r into L, that is the equivalent projected area into HC. What is HC? HC is just R. So, when you say HC, HC is the location of the centroid of the projected area, not the curved area. So, it is the location of the centroid of the projected area from the free surface. So, that is FH1. Is it towards right or left? It is towards right, because again you can see that its horizontal component is towards right. So, this is towards right, and then on CD, what is FH? First of all, it is acting towards left, its horizontal component. So, we put a minus sign, again rho G. What is the projected area? Into R into L into R by 2, which is the location of the centroid of the projected area, vertical location from the free surface. And so this is FH1 minus FH2, that is FH. Hence, you can calculate what is the resultant. So, these are two individual components, you can find out the resultant by vector addition. So, that is trivial.